A Journey Through Time, from H.G. Wells to the Stars. This journey is not just a flight of fancy but a deep dive into the realms of imagination and scientific inquiry. From the moment H.G. Wells penned The Time Machine, humanity has been captivated by the idea of time travel. His work opened the door to endless possibilities, sparking the imagination of countless readers and inspiring generations of writers and scientists. We've been enthralled by stories of journeys through time, visiting past civilizations and glimpsing the future. These tales allow us to explore the depths of human history and the heights of future potential, creating a bridge between what was, what is, and what could be. Movies like Back to the Future and Interstellar have further fueled our imagination, presenting time travel as a blend of scientific possibility and thrilling adventure. These films not only entertain but also provoke thought, challenging us to consider the implications of moving through time. But how much of this is fiction, and how much is rooted in scientific reality? The line between science fiction and science fact is often blurred, leading us to question what might actually be possible. The answer, like time itself, is complex and full of wonder. The universe is vast and mysterious, and our understanding of it is constantly evolving. Each discovery brings us closer to unraveling the secrets of time. The concept of time travel, once confined to the realms of fantasy, has become a subject of serious scientific inquiry. Researchers and theorists are delving into the mechanics of time, exploring how it can be bent, stretched, and even traversed. Albert Einstein's theory of relativity, a cornerstone of modern physics, provides the framework for understanding the nature of time and the potential for its manipulation. His groundbreaking work has paved the way for new theories and experiments. While the technology to build a time machine remains elusive, exploring the theoretical possibilities of time travel pushes the boundaries of our understanding and opens up a universe of fascinating questions. What if we could visit the past or see the future? How would it change our perception of reality? The human desire to unravel the mysteries of time is deeply ingrained in our psyche. It's a quest that drives us to explore, to learn, and to dream. Time travel represents the ultimate adventure, a journey into the unknown. We yearn to witness pivotal moments in history, to correct past mistakes, or to catch a glimpse of what the future holds. This longing reflects our deep-seated desire to understand our place in the continuum of time. While the practicalities of time travel remain a subject of debate, the very act of contemplating its possibilities expands our understanding of the universe and our place within it. It challenges us to think beyond the present, to imagine the infinite possibilities that lie ahead, and to appreciate the intricate tapestry of time that we are all a part of. To grasp the complexities of time travel, we must first confront our everyday understanding of time. Time, as we know it, is a constant companion, ticking away second by second, minute by minute, hour by hour. We perceive time as a linear progression, an unwavering march from the past, through the present, and into the future. This perception is deeply ingrained in our daily lives, influencing how we plan, remember, and anticipate events. However, Einstein's theory of relativity shattered this Newtonian view, revealing time to be a much more fluid and relative concept. His groundbreaking work showed that time is not a fixed entity, but can be stretched and compressed. Imagine time not as a river, but as a fabric, warped and stretched by the presence of mass and energy. This visualization helps us understand how massive objects like stars and planets can influence the flow of time around them. This is the essence of Einstein's groundbreaking theory. It fundamentally changed our understanding of the universe and our place within it. One of the key insights of relativity is that time is not absolute but is relative to the observer's frame of reference. This means that two observers moving at different speeds or in different gravitational fields will experience time differently. This means that time can pass at different rates depending on factors such as speed and gravitational pull. For instance, the faster you move, the slower time passes for you relative to someone who is stationary. An astronaut traveling at incredibly high speeds in space would experience time passing slower relative to someone standing still on Earth. This effect becomes even more pronounced in the presence of strong gravitational fields, such as those near a black hole. This phenomenon, known as time dilation, has been experimentally verified and is a testament to the mind-bending nature of Einstein's universe. Scientists have used precise atomic clocks to measure these differences in time passage. Another crucial aspect of relativity is the interconnectedness of space and time. They are not separate entities but are intertwined in a four-dimensional continuum. Einstein revealed that these two entities are not separate but are interwoven into a four-dimensional fabric known as space-time. This concept helps explain the behavior of objects in the universe on both large and small scales. This unified concept of space-time has profound implications for our understanding of gravity, the expansion of the universe, and the potential for time travel. It opens up possibilities that challenge our conventional notions of reality and time itself. While the notion of traveling backward in time remains highly speculative, and often relegated to the realm of science fiction, journeying into the future, though seemingly fantastical, has a solid basis in scientific theory and is grounded in the principles of physics. This is where the concept of time dilation, a consequence of Einstein's special relativity, comes into play. Einstein's theory fundamentally changed our understanding of time and space. As we've established, time is not a universal constant but rather flows at different rates depending on speed and gravitational fields. Imagine a spacecraft capable of reaching speeds approaching the speed of light. Such a vessel would experience time very differently compared to those of us on Earth. According to special relativity, as the spacecraft accelerates, time on board would slow down relative to time on Earth. This means that the faster the spacecraft travels, the slower time passes for those inside it. The faster the spacecraft travels, the more pronounced this time dilation effect becomes. This effect has profound implications for space travel and our understanding of the universe. If the spacecraft were to embark on a journey at near light speed for, say, a few years, the time dilation would be significant. Decades or even centuries could pass on Earth while the astronauts on board would only have aged a few years. This stark difference in the passage of time is a direct result of traveling at such high velocities. This phenomenon is not merely a theoretical construct, it has been observed in experiments with atomic clocks flown at high speeds. These experiments have consistently shown that time dilation is a real and measurable effect. While we are far from possessing the technology to achieve speeds that would allow for significant time dilation, the principle remains sound. The challenge lies in developing the technology to reach such incredible speeds. In essence, traveling at incredibly high speeds could be our ticket to the future, albeit a one-way trip. The journey would be a marvel of human ingenuity and scientific achievement, opening new frontiers in our quest to understand time and space.